So far, in our study of gases, we have been treating all gases as if there is no difference between one gas and another. We have treated every gas as if it were an ideal gas. To a great degree, this is true, as long as we are near the normal conditions that we encounter every day. Even then, however, we are aware of substances that are liquid at room temperature, but become gases at fairly low temperatures. This leads us to the questions: how are real gases different from an ideal gas? What conditions will make real gases deviate from ideal behavior? Is there a better equation than the ideal gas equation that can account for some of these differences? In this lesson, we will look at real gases and identify why and under what conditions they do not behave like an ideal gas. And we will investigate the van der Waals equation to see how it describes real gases better. The graph in this slide shows the behavior of 1 mole of various gases at various pressures. The ratio PV over RT should be a constant, and in fact be 1, according to the ideal gas law. But it is not only not equal to 1, but its value changes as the pressure changes. A similar graph could be made for each gas as the temperature varies. Real gases only behave like an ideal gas at relatively low pressures and relatively high temperatures. The question is, why? The ideal gas equation is based on kinetic molecular theory. In fact, it is derivable from the assumptions we made in the 5 points. However, the assumptions made in the kinetic molecular model break down at high pressure and/or low temperature. Both the high pressure and the low temperature are relative and depend on the gas. The specific assumptions that break down are these. First, the assumption that the volumes of the molecules are ignorable, which works when the molecules are far apart, cannot be made as we squeeze the molecules closer together at high pressures. Second, the assumption that the intermolecular attractions can be ignored, which works when the molecules are moving rapidly at high temperatures, is no longer valid when the molecules are moving slowly. Is it possible to produce an equation that will deal with these deviations? The answer is yes. In fact, we can modify the ideal gas equation to do this. This corrected equation is called the van der Waals equation. The first correction is made to the volume term, where what we really want, that is, the ideal volume, is the actual volume available to the molecules to move around in. This is the measured volume minus a correction for the volume that the molecules take up. The correction, NB, reduces the volume available to the molecules by a certain amount. The number of moles, N, is multiplied by the constant B, different for each gas, which is related to the molar volume of the molecules. The second correction is made to the pressure term. The actual pressure is less than we would expect if there were no attractions between the molecules, because the molecules attract each other away from the sides of the container and slow the molecules down just before they hit the side. This lessens the impact and therefore the pressure. The ideal pressure is a pressure that would be exerted if there were no attractions between the molecules. The A term is related to the attractions between the molecules, and the N over V term is the particle density. This is squared because the attractions are between two particles. If we solve the van der Waals equation for P, the most common way it is used, we get P equals nRT divided by V minus NB minus N squared A over V squared. The NB term makes the pressure larger, but the N squared A over V squared term reduces the pressure. This table shows the values of the van der Waals constants for a number of common gases and a couple of substances that are normally liquids at room temperature. This is the table enlarged a bit to make it easier to read. What factors influence the sizes of the two constants? Look at the noble gases. As we come down the column, the atomic size gets larger. The value of B also gets larger from neon to xenon. There's obviously something else going on as well with helium. This is also true of the other molecules, although this clearly is not the only thing going on. Think about the polarity of the molecules for the constant A. H2O is the only polar molecule listed, but CO2 and CCl4 have polar bonds, even though the molecules are nonpolar. Along with Cl2, these are the substances with the largest values for the constant A. We will look at other things that influence the attractions in Chapter 11. There are 3 problems on the problem sheet for this lesson. The first 2 involve using the van der Waals equation to calculate the pressure of a real gas. The third is an integrative exercise using the ideal gas equation.